last speaker of the symposium is Professor Cédric Villani, elected member of French Parliament. Cédric is an exceptional mathematician in every way. He worked on partial differential equations, Riemannian geometry, and mathematical physics. In 2010, he was awarded the Fields Medal for his outstanding work on the kinetic theory of Boltzmann equations and nonlinear Landau damping. He's my personal hero. He's equally well known for optimal transport, on which he wrote 2 very beautiful books. It's very unusual for mathematicians to be elected to a parliament. For many years, Cédric was the director of the Institute Henri Poincaré, made lasting positive impacts. He's a great spokesman for mathematics, to whom we are grateful. He also wrote a popular book, The Birth of a Theorem. Today, we are very pleased to listen to him on a topic to be announced by himself.
Thank you, Shumei. Everybody hear me? Including at the back? Yes, thanks a lot. And it's really a pleasure to be here, part of this event. Also to be part of an event which is associated with the name of De Moivre. And I will also explain why he's one of the examples that I use a lot in my public speeches. And first, let me explain why the reason of the image. You know, I had scheduled to give a handwritten talk, and when I arrive, I discover that there is only this. And they told me to put beautiful image, so I put this image, which I like. For several reasons also. First, it shows that, it reminds us that mathematics can lead you everywhere, because it was during a mathematical conference in Algeria that there was this beautiful trip in the Sahara Desert. And actually, that's one of the great things of mathematics, that it makes you travel so much. And also, this talk will be about the journey, you know, the road, and how about the fact that you should not have too precise plans of where you are heading to when you are doing research. Maybe it's good to take your time or to go on a side way or whatever. Let me also insist that one of the reasons why I decided to go for handwriting is, first, I love the old-fashioned handwritten talks, and secondly, the beautiful computer talks like we've seen today require a lot of time in preparing. Yeah, you can do a talk that is 10 times better with the computer, but it will require you 100 times more preparation time. And you know, when you're a politician in parliament, you have so little time. So during this week, I had to go to China. You know, I was part of this presidential visit in China. In total of 3 days, I slept a total of 7 hours. You know, there were all kinds of things to do everywhere. It's impossible to focus on the talk that you have to prepare when you are in such precipitation, you know. So it had to be a talk that is not very much prepared. It will be a bit of a messy talk, but I hope it will not be a big problem. And hopefully it will also be incitation for a question and interaction. Also, I understand that there are some very young fellows around there, yes, from the high school, yes. Now, people, you are the hope of the nation, we count on you, you are the future, etc. You are the best, and this talk will be in large part, aimed at you. So that I will try to be not too technical, but I will insist. I will tell you about the subject, but also about how I came into the subject, how I changed direction, etc. So a title could be Suboptimal Road Through Optimal Transport. The subject is optimal transport. Okay. I will have to write big so that you can all see, right? Optimal transport is a problem by which you want to have some object that you want to transport from one place to another, and you want to do it in the way that is most economical. And in the original formulation, which goes back to the 18th century, it was something like this. Assume that you have some pile of some earth to dig, and you have to reconstruct it in some kind of way, you know. And how will you transport all the material, this from here, this from there, etc., in such a way as to spend the least amount of energy? It was a very practical problem. It was an engineer's problem. But it was an engineer's problem which was set by a guy with a very strong mathematical spirit. This was Gaspard Monge, same guy who played an important role at the science at the French Revolution, who was one of the founders of École Polytechnique, etc. And it's one of the examples of great mathematicians who were able to think in very theoretical ways, but also with very concrete problems in mind, and that has been very enriching. So that is the subject I will talk to you about. I wrote 2 books on the subject, which Shumei was very kind to mention, and I'm very proud of having written these books, enormous amount of effort of synthesis. But I will tell you about a suboptimal road to go into this subject, because the directions which it took for me were never directions which I intended at first. And let me explain you about this. So some of the keywords that will be going through this talk are the power of meetings, international travels, local and international interactions, the power of chance. You know, in research, is advice for the young people, one of the most important things is how you recognize when you are being lucky and how you exploit your pieces of luck. I had enormous pieces of luck in my career, and the fact that I was able to spot them and use them was completely instrumental. Unexpected developments will be important. And also a theme which I like is always teach. Even if it's for research, it's good to teach, including teaching stuff that you don't master yourself. So let me go through this, and let me give you a more precise definition, but only slightly more precise. So imagine that you have a distribution. It's the same picture, except that on this side, instead of putting it like inside the ground, it will be something like up the ground. Something like we are transporting an amount of material like this to something like this. Let's call this a probability measure mu0, and this is probability measure mu1 on some space, whatever. And assume that when you have a unit of mass here, you have to give a certain effort, a certain amount of work to transport it to another position. And that will be the cost of transportation. Maybe here this is position x0, this is position x1, and this will be the cost to go from x0 to x1. People in the back row, is it okay if I write at this side? Yes, thank you. So every time, yeah, always, this is number one thing. If people don't understand what you are saying, this is the talk is lost. So, and each amount of matter that you transport, you will pay this cost. This is the intuitive way to formulate it. There are several rigorously mathematical ways to formulate it. One way is like probability, to say that you want to minimize the expected value of the cost to go from this is the cost C, this is random variable x0, this is random variable x1, and you want to do this of all possible couple realizations of x0, x1, such that the law of x0 is equal to mu0, so that is the distribution of x0, and the law of x1 is equal to mu1. That is one possible way to mention it, to state it in probabilistic terms. And let me give you another way, which is equivalent. This will be, let's write it this way, minimum of double integral of c of xy squared pi of dx dy, where this is a joint probability measure. Imagine that this is the space of x0, this is the space of x1. consistency. I should write this like x0, x1, dx0, dx1 will be better. And imagine I see probability measure here. It's like, you know, some continuous distribution there. When I integrate in this way, I see mu0 sitting here. When I integrate in that way, I see mu1 sitting here. And I think of this joint distribution measure as a plan. If I'm an engineer, this is the transportation plan telling me every time I have some mass x0 here, how much I should move from this place x0 to this place x1 so that the transport be as efficient as possible. Okay, there are other possible ways to reformulate this problem, but so far you have the idea. So it tells you that it's about the optimal way to transport one probability measure to another. So it's part of probability measure if you want, but it's also part of optimization because you want to make something as small as possible. And it turns out it can also be recast as a problem in geometry if you put some geometric features here in the cost x0, x1. So for instance, if you work in a, why did I put a square here? Sorry, there's no square. But very often, the cost that you will put will be something like x0 minus x1 square distance, if it's a norm, if you are working in the Euclidean space, or if you are working in a geometric setting, it may be distance from x0 to x1, or distance from x0 to x1 with a power 2, or with a power p. And these problems has turned out to be extremely efficient also to work out in geometric context. Actually, in geometry, you know, maybe the most basic concept of geometry that goes beyond Euclidean context is one of geodesic. What is geodesic? You have one point, another point, and you ask which is the shortest path to go from this to that point. So it's an optimization problem. It's part of calculus of variations, and that's the basis of geometry. So also here, it's an optimization problem in which I am minimizing. And actually, you can see this thing as a kind of geodesic problem in which probability theory is incorporated. So mixing the geodesic idea with the idea of probability measure. How did I go into this subject at first? Let me tell you, because as Shumei mentioned, I was trained in partial differential equations and kinetic theory, which is theory of gases and plasmas. And it turns out that in the 70s, a Japanese mathematician named Tanaka had showed the following. Okay, never mind. It doesn't distract you too much, this, no? Okay. So Tanaka had said the following. It was in the 70s. If you define W2 of measure 1, measure 2, to be the square root of the optimal transport cost to go from mu0 to mu1, you know, that is solving the problem of transporting mu0 to mu1 most efficiently possible, when the cost is equal to x0 minus x1 square of the distance. That is, you pay a very high price when your particles are far apart. And this is in Rd. Maybe R is equal to 3. And this you have to think of in physics as the space of velocities. Then when you look at a certain kind of Boltzmann equation, which is the equation describing gases, you see that as one of your solutions of the Boltzmann equation evolves with time, let's say mu0t as time goes, and the other will be mu1t as time goes, two different solutions evolving with time through collisions, making the probability distribution change from time to time, then you will see that the distance between mu0t and mu1t is a decreasing function of time, so that your two solutions become closer and closer to each other. And why was Tanaka interested in this? To give a new solution, a new proof of one of the most basic facts in kinetic theory, that is, when you let a gas act through collisions between the particles, then the probability distributions of velocities converges to a Gaussian velocity, to a Gaussian distribution. So he was able to give a new proof that for any solution of the Boltzmann equation, probability distribution of velocities as time goes to infinity, it will converge to this familiar bell-shaped curve like the Gaussian. You know, we call this curve Gauss, but who was the first to discover it? De Moivre, yes. And that's the connection with De Moivre here. And De Moivre discovered it like it was a very unexpected theorem, like maybe the first very advanced theorem of probability theory. When you look at, say, a game of heads and tails, and you throw up your coin in the air and you count the heads and the tail, you know, on average it will be 50%, 50%, but you can look at the error. The error will be smaller and smaller as the number of trials increases. And when you see what is the distribution of that error, if you make a zoom so that it gets fixed as the number of trials increases, you will see a beautiful Gauss distribution, a beautiful curve like this, with an equation that is something like constant exponential minus v squared divided by something. And De Moivre was the first to get this very particular function. You know, when we learned the beginning of probability theory, we were told about the law of large numbers. It's not obvious to prove, but at least it's intuitive. You know, if I throw my coin in the air many, many times, it will be 50%, 50%. A child can believe this. But why does this come from? No child will understand where it comes from. It's really advanced and unexpected. And that's one of the great things De Moivre did. Apart from that, De Moivre is a great example because he was a French Huguenot, you know, from the Protestants, and he had to escape from France after when the Nantes treaty was revocated by Louis XIV, and there was religious persecution. And it's a great example of the talent that you can lose when you have an approach which is not tolerant and when you start segregating people and so on. So it's a lesson we should never forget. When you start to put barriers and prevent the freedom, you are losing talent to the outside world. Okay, that is for De Moivre. Let's go back to Tanaka and Boltzmann equation. So far, so good? I told you it would be a little bit confused, but anyway. So I was a student and very interested in this, and I happened to discuss with the supervisor of studies in École Normale Supérieure when I was. His name was Yann Brenier, and it turned out that Brenier was interested in this same kind of optimal transport thing, but for completely different reasons. He was an expert of fluid mechanics, and in particular incompressible fluid mechanics, working on the Euler equation and trying to construct some weird solutions of Euler equation. And he had found out that by using in a clever way this optimal transport problem of Monge, he was able to construct unexpected solutions of the Euler equation. And so we started discussing with this, and he told me, wow, that is great, and it's very funny because there is a lot of work currently on this optimal transport problem. And he showed me a paper. He told me, yeah, you know, this is a young German guy. His name is Otto. He's working on this kind of problem, also from partial differential equations, but from a completely different perspective related to heat diffusion equations. And then we started discussing with this Brenier. At some point, he said, why don't we organize a conference together in which we will discuss about various aspects related to this optimal transport thing? I said, yes, of course. Of course, I had to organize a lot of things, but it teaches you a lot also. And I did not present my own work. Instead, I rather explained the work of Tanaka, even though it was decades old, and I explained how it was interesting in perspective, etc. And Otto presented his stuff about how you can use optimal transport to get a new point of view on the heat equation. And I listened to his talk carefully. It seemed a bit abstract. It seemed a bit weird. It was different from all the other talks, and we had a good discussion. And now, a great piece of luck, which one of the best pieces of luck which occurred to me later, was that a few weeks after that, I was happening to be reading a course on probability theory by Michel Ledoux from Toulouse. One of the advisors in my jury, a specialist of Boltzmann equation, had told me, take a look at the Ledoux work. It's not your PhD theme exactly, but maybe it's related. You will find some interesting example in there. So I started to read the Ledoux book, and I thought, wow, this is fantastic problem, and so on. And at some point, I see one of the theorems that was explained by Ledoux. It was theorem by Talleyrand about so-called concentration of measure, and it was a certain relation in certain spaces equipped with probability measures. Relation with the optimal transport problem, with the entropy problem, which is a way to measure the disorder in the Boltzmann framework, and with the so-called measure concentration problem, which is when you have a probability space and a certain set, say probability 1/2, and when you enlarge this set, how fast do you increase the probability measure? And there was a result by Talleyrand, which was explaining how it was related, giving some relation between this. And I looked at this result and I thought, there has to be a connection with the talk by Otto, which I heard a few weeks ago. I am sure there is a connection. It's often in mathematics that good ideas come from connecting two things. And indeed, it took me about, it took me a quarter of an hour to find a connection, but it was wrong. It's very often the case that our first tries are wrong. Then a bit more work, and I found the connection right, even if it was formal. And then I rediscussed it with Otto, and we published a paper together, which was not about a new theorem, but about a new proof of a theorem which was already known, plus some extras. Stated in this way, it was not a big deal. I am exaggerating a little bit. There was quite some work, but it was, work of a week's worth of work, something like this. And my friends, this is my most quoted paper of all my career. Not that it is the most important. One should not. It's not that your paper is the most quoted, that it is automatically the most important. Neither way wrong, neither way. But still, I think this paper had some importance, and it came from piece of luck and from the fact that I was attending these two events, none of which was directly connected with my PhD, but having some kind of relation. Another thing which was important in the Ledoux course is that this is the first place in which I heard about the Lévy-Gromov isoperimetric inequality, which I will explain about, and which I was fascinated by immediately. So let me, before I go into this Lévy-Gromov, let me mention the sequel. And again, it will be the kind of joyful, chaotic randomness that can happen to you in the career. We found with Otto this proof of new theorem. I will not tell you exactly which theorem it was, but anyway, at a short distance from that, I was invited in Atlanta by Eric Carlen, who was a member of my jury, and expecting me to present some results about Boltzmann equation. And when I arrived at the seminar, I talked of Boltzmann equation, but I also talked about the work that we did with Otto. It was a good piece of chance that in the audience, there was Wilfried Gangbo, who was a specialist of optimal transport, and who thought, wow, this thing is completely new. And he was an expert on the subject, but he was very much excited by this, and he thought there is something that we have to make further. And we got along well together with Wilfried. So he arranged that I could come again and spend one semester in Atlanta for being a visiting professor. I said, of course, yes, I want to come. And what should I do? And he told us it would be great if you could teach us a course on optimal transport. Now, to make sure, at that time, I only had one small contribution to optimal transport theory. But the great majority of the theory, I could not claim to be an expert in any way. So the natural situation would have been something like, I'm not an expert in optimal transport. Let me make a course on Boltzmann equation, and I will perfect myself in optimal transport with you, and then later we can see what we can do. But instead I said, yes, I will teach optimal transport. My friends, teaching is by far the best way to learn a subject. So I spent a semester working out this course in Atlanta about optimal transport, preparing my course, etc. And in the end, this course became my first book on the subject, which became the first reference textbook, kind of, in the field. And after teaching this course, I could say, okay, now I'm an expert. I've read these dozens and dozens of papers. I know the various proofs and making developments, etc. And the story doesn't finish there. After that, there were a few developments. But you see on this example the power that can have on your career, the various encounters, the randomness, the exchanges, and the ability to be ready to teach. Now, let me tell you a bit more about Lévy-Gromov, and this will be the transition to the sequel of the talk. Many of you, maybe most of you, maybe all of you know about the isoperimetric inequality. Isoperimetric inequality, the classical one, isoperimetric inequality, is something that tells you what? Say you are in Rn, and it's a Euclidean space, and you are considering a certain set with a certain measure. So maybe this set is A, and it has a certain Lebesgue measure. And you will consider the ball, the Euclidean ball, which has the same measure. Let's call this alpha, and let's assume that this is the ball B with the measure that is equal to alpha. The volume is alpha. Then, if the volumes are equal, then the measure of the surface of this, has to be at least the surface of this. So let's write it like surface of A is bounded below by the surface of B. It's a very powerful principle, and you know it's used to explain about the shape of bubbles, because in the bubble the quantity of air inside is fixed, so the volume is given, but the energy is minimized when the surface is as small as possible, so that's why you have round bubbles, etc. It's one of the most fundamental inequalities in geometry, so prototype of geometric analysis, and it's the motivation of many, many developments. Now, this is a theorem about Euclidean geometry. What can we say about non-Euclidean geometry? Then there are a number of possibilities of ways to generalize this, but one of the most satisfactory is the following, and is known as the Lévy-Gromov isoperimetric inequalities. Okay. So what does it say? Take an n-dimensional geometry, Riemannian manifold, as we say. So you have this geometry with this surface or generalized surface, maybe in many dimensions. Let's call it M, and it has dimension n. And on there is a way to measure distance, which is the geodesic distance. There is a way to measure the volume. There is a way to measure the surface, etc. And you are taking a certain set. Let's call it A. You know, maybe it's a messy set. It's a part of your manifold. And let's assume that the volume of A divided by the volume of your manifold M is equal to alpha. So it's maybe if alpha is half of the set M in the sense of volume, alpha will be equal to 1/2. And okay, you want to compare it with some other sets in some other geometry. If your manifold is something very irregular, whatever, it doesn't mean anything, the notion of a particular ball. Okay, you may define a ball as a set of points which lie at a certain distance from a point, but it may be very messy too. Instead, the path which non-Euclidean geometry has chosen to go is by comparing it with a sphere. So this will be a sphere, and what you will try to compare the situation to a situation occurring on a sphere, with the idea that the sphere is maybe the most simple non-Euclidean geometry that you can think of. Now, to define a sphere, you need to know about the dimension, and you need to know about the diameter of the sphere. Equivalently, you need to know about the curvature of the sphere. You know, if it's very small, the curvature will be high. If it's large, the curvature will be low. And here, the diameter that you like, the radius that you want to take, will be square root of n minus 1 divided by k. And this k here, you take as a lower bound on the curvature here. Curvature of m being bounded below by k. Here, let me not be very precise about this curvature. The correct meaning of curvature here is the so-called Ricci curvature, which is famous for its ties with general relativity and also the fact that it appears everywhere in certain branches of intersection of probability theory and geometric theory. Actually, whenever you have problems with some kind of isoperimetric content, you can be sure the natural curvature involved would be the Ricci curvature. So, and what you do is this. You consider the ball here, B, that is set of points which are at a distance which is no more than a certain radius from a certain point here. And you choose your ball in such a way that the volume of the ball divided by the volume of the sphere is equal to alpha also. Okay, so it's the same as having the same volume that we saw before. And then what the theorem says is that if this situation is correct, then the surface here of this set is not less than the surface here of this ball. So the surface of this divided by the total volume, okay. Of course, I should have made some compromise about the, yes, this way it will be okay, maybe. So the surface, let's write it this way, of A divided by the volume of M is bounded below by the surface of the ball B divided by the volume of the ball B. So you see, it really sounds like the isoperimetric inequality that we saw in the Euclidean case. But it's a non-Euclidean version. It's sharp in many respects. It's really, let me say that it's really a beautiful inequality. First guessed by Levy in the 50s, probably with a proof that was non-rigorous, reproved by Gromov in the 80s, which a proof that was rigorous, but that was a bit crazy. Pascal, question? Yes? Alors, sigma, oh, this is S. Thank you, Pascal. Okay, contradiction is important in our field. And it's the basis for a number of developments. Actually, Levy was interested in this precisely for same kind of stuff that Talagrand was interested in, problem about measure theory. Because, for instance, once you have an information like this, concentration of measure, once you have an information, if you know an information about the volume of this set A, it implies information on the surface. Then when you increase the set by enlarging it, the information of the surface will imply information on how fast the volume of the set will increase also. So it will be part of the same problem of concentration of measure, which Levy is considered to be the founder of. Many applications, so in probability theory, etc. The proof by Gromov was beautiful, but natural in a way, but resting on very, very sophisticated tools. Tools about geometric measure theory that you don't want to hear about. Let me just say that the first step of the proof is to find a set A which is optimal, which achieves the worst possible situation in the inequality. And it's like finding a solution to the isoperimetric problem. And these problems are known to be extremely technical, relying on huge proofs. And okay, we can use these big black boxes and be happy with it. But we may also say, come on, if I use a very sophisticated tools, it will be difficult to generalize. It will be difficult to optimize or change the parameters. It will not adapt to more general situations. Maybe it's not, for instance, if you replace the smooth geometry that is here by a non-smooth geometry, the proof breaks down. For instance, if you want to put some errors, it will break down and so on. And so you would like also to find a better proof, better in the sense that it is more elementary, more elementary, meaning that you control all the parameters, that you can generalize it to a non-smooth situation, etc. And from the start, for many years, it was considered, let's try to find a solution of this which is based on optimal transport theory. Now, I never myself tried to be involved in this kind of thing first by myself until in 2004 in Berkeley, I met American mathematician John Lott. I will say it again, kind of circumstances, which is interesting. I was there in Berkeley as a young professor, visiting professor, under the hospitality of the Miller Institute, with a beautiful visiting program in which there was no research obligation, no teaching obligation, and no administration obligation. All I had to do in the Miller Institute was to have lunch once a week with the other fellows of the Miller Institute and tell them about what I was doing. Yes. For this, I was paid 3 times my French salary. And it was a kind of good conditions in which people understand that it's good to have you near the place to participate in this and not to put too much constraints. However, Berkeley environment was tough for the young professor that I was because very high-profile research department, many famous researchers, very, very busy all the time. And I was there wondering, what can I do? What kind of collaboration can I do? In the end, I ended up collaborating with another guy who was also a visitor there, not one of the Berkeley people. He was there by chance. His name was John Lott. And one day he arrived in my office and told me, oh, I read your paper with Otto, and it's very interesting what you did, and we are going to do some fundamental work in geometry with this, with a new definition of the Ricci curvature that is based on optimal transport. I said, what, really? I didn't know of all his problems, and I had to learn about what he was saying, and this was the start of me going into Riemannian geometry, as you said. Very important also is that by that time I had spent a few years already in the École Normale Supérieure de Lyon research environment, in which I moved in around 2000, in which the spirit was much more multidisciplinary in a way than what I had known before in Paris. And the fact that I was able to go into geometry, the fact that I went into this was also psychologically, at least due to the fact that I was discussing in Lyon very often with the geometers, much more than I had been discussing with the Paris geometers. Advice for young people, change environment from time to time. It's not just the specialized skills that you get there. It is different spirits. Some places will be very good at some kind of collaboration, some places will be good at other things, and depending on where you are, you feel differently what you are able to do. So together with Lott, we started developing things and the theory of how to deal with curvature in a way that is not based on the fancy differential geometry, but based on probability theory, basic probability. And here is the definition which we worked on together with other people about the curvature. Let me give you this definition. Imagine that you have a space. This is a metric space, so this is a distance, and this is a measure, okay? A reference measure, like the Euclidean measure, maybe if we are in Euclidean space, or the volume measure if we are in a non-Euclidean geometry. And we want to know if this space is curved, and let us say that we want to know if the curvature of this space is non-negative, okay? And we want to do it in a very elementary way that we may be able to explain to physicists without using any sophisticated notion of differential calculation or whatever. Just a bit of measure theory and probability. So here is a way to do. Here is a way to define it. We will say that imagine that you have a transport to do on this space with one probability measure mu0 and another probability measure mu1. You recognize this situation. And I transfer the measure, I move the mass mu0 to the mass mu1, you know? And in a way which is as economical as possible, as efficient as possible, with a cost function that is c of x0, x1 is the distance from x0 to x1 to the square. Okay. And all along the way, I do this interpolation, going from m0 to mu1. So it's as if I am choosing the optimal way and transporting, continuously from time 0 to time 1 this thing, with each particle going from the initial position to the final position with a certain, along a geodesic way. And all along the way, the probability measure will change. So maybe assume this is viewed from the, let's say this is viewed from the top. I mean, maybe I put here, this is my geometry here. And I'm seeing here, maybe there are places of high probability, low probability, and this is mu1. And all along at intermediate time, between t equals 0 and t equals 1, at maybe half time, it will be a different distribution of mass because all the mass has gone halfway. And I look if this mass is spread or not spread according to the good old laws of kinetic theory of gases, which tell me if the distribution of velocities is very much scattered or not. And for this, we know that the good formula is the Boltzmann formula, that is the entropy of the distribution mu is the integral, is minus the integral of rho log rho d nu, where rho is the density of mu with respect to nu, the density of the gas. So I look at this quantity, which when it is very high, it means that the gas is very disordered, the distribution is very much spread. When it is low, it means that the gas is quite ordered, distribution is concentrated. And I look at the evolution of this measure of disorder over time. And if the curve of S is always a concave curve of time, it means that I am in a curved space, a space that has non-negative curvature. And the intuition behind this is that in a space of non-negative curvature, geodesics typically start by separating out and then they converge again, so that the gas can afford to be more spread at intermediate times because the geodesics are more spread. And that is the basic intuition behind it. You can translate it in complicated, rigorous mathematics, etc., but all that is technique. Most important is the first illumination, like we are going to use this way to encode the curvature. And now that is interesting because this is very robust notion. For instance, you can define it even if you have no differentiability, even if you can't write down the differential equations of the geodesics. And it's very stable. If, for instance, you make some perturbation, the picture will be perturbed again. And if you have a limit situation of geometries which are curved this way, it will also be curved this way. So in this way, together with John Lott, also at the same time with Karl Theodor Sturm, we could prove some basic problems which were not known before. Something like, for instance, assume that you have a family of geometries converging to a limit geometry, let's say like this. And you know that at each step, the Ricci curvature of this is non-negative. Does it follow that this also has a non-negative curvature, even if the convergence is very, very wide? Answer is yes. But to prove that the answer is yes, we had to first reformulate it using the formalism of probability measures, optimal transport, and the entropy. And this is an example of how a problem can be solved in a completely unexpected way. You think it's a problem of just geometry, and then the people will come with a solution that uses the entropy, the intuition coming from the kinetic theory of gases, etc. That's an example of unexpected road taken by the research. Okay, where am I with the time? Yes, beautiful. We will keep a bit of time for questions. Now, this field, this connection, turned out to have a lot of potential. Many people starting to develop it. Dozens and dozens of researchers started to explain, to explore the connection between the optimal transport, the curvature. It has become very difficult for me even to follow the developments. Last year, or maybe a couple of years ago, I gave a seminar on one of these developments, which was precisely the solution of the problem I was talking to you about, using optimal transport to prove, to give a new proof of the Levy-Gromov isoperimetric inequality. And a proof which was exactly as we wanted it to be, that is, a proof that was robust, elementary, giving way to generalizations, opening path to new understanding, and so on. I wish it was my proof, but that was not the case. And the proof was given by Cavalletti and Mondino after some very important connection by Klartag. And it's a long story, but full of connections. But just to tell you one thing that was a key. So all these guys, what they did is give a new proof of the Levy-Gromov. So based on optimal transport, a proof which was robust, general, applying in non-smooth context. When you try to come up with such a thing, you think about it and think hard, and soon you discover that it doesn't work. It can't work. You see, the classical proof of the Levy-Gromov inequality is based on first finding a set which is best, and then looking like you are making imagine you are starting from this, and then you will make a foliation, a kind of partition of your space based on this interface. For every point which is here, you look at the point on the boundary which is closest. Let us say that this is like this. And this point here, you see what is the point where it is closest. Think of this like the orthogonal projection on the boundary. And you will cover your entire space by this kind of lines in which you have these all through these closest approximation. That is the classical proof. And then you ask, how am I able to connect this with optimal transport? And it doesn't seem to work out. Because this is like a partition of the space into lines along which something occurs. And in optimal transport theory, it is known that such a partition occurs when the cost function is the distance. It was already known to Monge. But it was also known by experts and very well known that all the good applications in Riemannian geometry came from cost function to be distance xy square. And it's not the same thing, of course. And so you always ended up like, if I choose this, it will, but this not either. Until Cavalletti, for another purpose, understood that in some situations, solving both problems are equivalent, and that you can kind of prove the theorem reducing only to cases in which the two are equivalent. Just this psychological change, saying there is a situation in which both problems are equivalent and it's sufficient to work out. An expert who knows this would be able to go through the proof, to reconstruct it, etc. But just this information was very important and very imaginative. And the other thing, which was due to Klartag, was a connection with another of two pictures. You see, in the Monge picture, it's like let's do transport, and transport will always occur through lines which don't intersect each other. It was known from the start that if you do transport cost, say in Rn, with cost which is like x minus 1, then the lines can never cross. Otherwise, if this is transported to this and that is transported to that, it would be better to do this and this. Okay. So, in all people studying cost function like this, they were doing this picture. And people in convex theory had something that they called needle decomposition, which is a way to study some convex inequalities doing a partition of things into lines which do not intersect. My friends, it's the same picture. But to realize that it was the same picture, it took somebody who knew about this and that was the case of Boas-Klartag. And he understood that you could use this problem to do an intrinsic way of this needle decomposition that the people in geometric convex theory were very much used to. It's another example of the fact that having one foot in one field and another in the other field can give you keys, illuminations about what to do. Now, after these two strokes of very great imagination, technique could come and come and come and come, and then the problem was solved. And then it occurred that unexpected developments of a field in which I was involved for various reasons turned out to solve that problem. Now, these are just some examples of the many, many applications that optimal transport theory had over the past decades, and which are, surveyed in my books. Some of these fields are computer vision, or financial math, or meteorology, or at some point, for instance, people found out that you could find some optimal transport interpretation behind the famous Perelman proof of the Poincaré conjecture. Peter Topping in the UK is one of the main experts in this, for instance. Many, many things. And it so turned out that it's even more, even me who have been in this for quite a long time, I'm still amazed by how much it goes into. So it will be the connection with my current activities, and with one of the themes of these things is a connection with the very famous artificial intelligence business. So let's talk a bit about artificial intelligence. I've been missioned by the government for a report about the French strategy of artificial intelligence, which means that every day for the past 3 months, let's say, I've been eating artificial intelligence every day. Eating meaning discussing about people, understanding what the economy is about, how are the applications here and there. I just had a wonderful discussions here with people from Imperial and people from DeepMinds here to understand about that. And let me say that I, like most of the other people, I did not expect at all that it would become such a craze, the artificial intelligence. When I was a kid, when I was a teenager, I was a huge fan of Douglas Hofstadter. I'm sure some of you have read his books, like Gödel et Scherebach and so on. And I was fascinated by these pieces in which he was talking about artificial intelligence, programming Lisp and whatever. Probably part of my passion for some parts of mathematics came from there. But later, when I went into research, I went into PDEs, I went into mathematical physics, and like many other people, I thought that artificial intelligence was quite soft, not many big results, etc. Actually, when one of my collaborators on optimal transport, Yann Olivier, moved to artificial intelligence, I told him, are you sure what you're doing? It doesn't seem to be very efficient, artificial intelligence, these days. Of course, was completely wrong. And I was completely wrong, and I had not expected and seen the turn that it had taken. And as we know, it became more and more famous. And in 2015, I had the surprise to... So let's also say that whenever I had a problem about some artificial intelligence to explain, about broad audience or whatever, I would take out my phone and call Yann and ask him, can you explain me about this or this and that? This is also one way why people who move from one field to another are very interesting. And 2015, I was invited by the COLT people, the computational learning theory people, for the big meeting that they were organizing in Paris. I received the invitation. I thought, gosh, why are they inviting me? I'm not an expert at all. So I called Yann. Why do you think they are inviting me? And he told me, well, we don't know, but these are very good people. If they are inviting you, they have some plan, whatever. And he said, maybe it's because of the similarities with some of the keywords, etc. And of course, I accepted the invitation, even though I knew nothing about learning theory. But my talk sounded familiar to them. Their talk sounded familiar to me. I recognized many ingredients when you go into the technique. Convex optimization things, probability theory, some of the big tools and so on. They really looked familiar. I had good discussions, many possibilities of intersection and collaboration maybe that I had to taken and there. And a couple of years after, there they are. Not that I did anything about it, but the connections are there. And it is my great surprise and great pride to see that my books are now quoted in many papers about learning theory in which the connection was made with optimal transport. Let me say that this is very recent research. Actually, a bunch of papers appeared in Proceedings or in preprints in 2017. Some of the names, some of the people there are okay. At first, there was precursor about by Zhao, Mathieu, and Lequin. The keyword is generative adversarial network. I will tell you a bit later about the idea behind this. And some of the people who worked on more explicitly the connection with optimal transport are Arjovsky, Chintala, Button, Ahmed, Dumoulier, Courville, Guo, Hong, Lin, Yang, Lei, Su, Kui, Yao, Gu. Yao is Yao Xingtung, the famous geometer. All the people who did the explicit link are either Chinese or American or Canadian, which are three great nations about artificial intelligence. And I very much like the idea behind. So let me, to just give you an idea of what it is like, let me sketch the thing. So, yes. Absolutely. You know, politicians become very talkative. Now, you know, when you have a neural network, the big thing is you want to reconstruct some unknown function. You have a function which maps some input to some output. You know a lot of pairs like input-output, and you want to guess what the function is. And you want to guess a function which doesn't depend on many parameters, just a small number of parameters that you want to explain. Okay. And in the generative adversarial network, adversarial learning, which Yann Lequin described to me as one of the very best ideas which occurred in the field in the past 10 years or so, it's like you have two neural networks. One which tries to reconstruct, let's say you have here, this is something which depends on a small number of parameters, let's call this Z, it's a small space. Here you have a huge space, many, many parameters maybe, and some observations there. And you want to construct these observations, say as a function of this, which is transporting some given measure on this space F into some probability measure there, which you want to be as close as this to this as possible. That is, you want to reconstruct the characteristics of the observation from a small number of parameters. And now when it is adversarial, you have a second neural network which is acting against you, trying to trap you, and which is trying to recognize whether this is different from this, and trying to recognize from a sample whether it comes from the true sample or from the copy that you are trying to make. And they are trying to trap each other. This guy is trying to make things that are as undistinguishable as possible, and the other guy is trying to find the differences and focus on there. It's a bit like, you know, when you have the teacher and the student will try doing his best to reproduce the technique that the teacher has given, and the teacher will figure out some exercises that will trap the student. That is something that will resemble the thing, but there is a trap somewhere. And little by little, they exercise and go to the optimal. And now the idea, which takes roots in work by Lequin, but then was developed explicitly by these people, including Yao and so on, is that you can measure here the distance between these is very efficient to do it with a transport metric approach, with one of these W functional that I told you. And that, in fact, this problem, when you take certain cost functions to measure here the discrepancy, taking the geometry into account, these problems here, the adversary and the original, they are like a dual problem, exactly as in the optimal transport problem. We know there is a primal and a dual problem. One is about minimizing the transport cost. The other is about finding how to find prices which are optimal in some sense in the transportation way. Let me show you. This will be my only use of the computer. Let me show you how these papers look like. Okay, this is one of these early papers about the energy-based generative, etc. One of the beautiful things about this technique is the images that it produces. Quite amazing. These are kind of images that look weird, but they look realistic. When you look at them from a distance, you think they're okay. When you look at them clearly, you see there is something which just doesn't work. We will see some example with animals in another paper. And here is one of these. You see Wasserstein is one of the key words for this optimal transport. Kantorowicz-Rubinstein duality is another problem, is another way for the optimal transport thing. And this is this paper that, one of these papers, Facebook also is involved, in which they use the optimal transport problem to do their adversarial network training. Let me try to get you, yes. This is a geometric view of optimal transportation and generative model. So bringing together the two fields. This is the picture I was telling you. Wasserstein generative adversarial networks. And why is this interesting? Basically, first they say they have a method and they show that their method is more efficient in some sense than one was done before. Secondly, it gives you a connection. Connection gives you a way to eliminate both sides and also gives new ways for people to enter into this. Let me see with these. Gosh, I wanted to show you some of these crazy images. Ah! Okay. Ah. Yes. These are some images that Yann Lequin and other people, for instance, show in there. Oh, resolution is not so good. Okay. Well, I told you this talk would be a bit messy. Anyway, please, those of you who've not seen it, Google up or Quant app generated adversarial networks, images, and you will see these creepy images in which you have shapes of animals that from a distance they look like familiar, and when you look closely they look like they are not wrong, something is wrong. These are images that have been divided especially to trap the neural network which is trying to recognize the animals. So I don't know exactly what is behind in these papers in more detail, but I tell you, my friends, next year I will teach this. Okay. Okay, that's all, folks. Thank you.
Thank you very much for the fascinating talk. I'm sure there are lots of questions. One hand already raised. Yeah, we have some time for questions, please.
Thank you so much for your talk. I just wanted to say that now basically optimal transport is being used to train the network. So it's a development that came from GANs last year. So is it a subject that you're going to work on next year? Or do you teach it?
You know, one of my problems is that I want to work on everything. And at the end, but since at the end I am also working in depth, in the end I can do much, much less than I would like to do. But this is subject I was intending to start a PhD thesis in collaboration with Facebook Paris AI research. We had talked about this with some of the guys in FAIR.
Yeah.
Errol.
Related to reinforcement learning, I was just wondering if your optimal transport wouldn't have a reinforcement learning type solution where you'd be doing samples and then choosing among them the best ones and so on, progressively moving forward.
Mm-hmm. Algorithmics of solving the optimal transport is a bit of a mess. And there is quite a contrast between. Okay, first, it's only recently that some efficient methods have appeared, and I am not enough expert to answer your question with certainty. But so far, there are not really of that. I mean, there are. iterative methods, as in many ways, when you have a duality problem in which you go back and forth between the primal and dual problem. Some of them uses some gradient type techniques and so on, but it doesn't sound like reinforcement learning to me so far, but you never know. One of the young people there.
Okay. One of the young people, if you consider yourself young, whatever age you are, allowed one question. Nobody's young.
Yeah, I can see they are working on that. Yes? Yes.
Oh, yes, come on.
Oh, hold on. Let me come get closer.
So you said you talked about your work scientifically with Facebook, and so you talked about number theory and how you like to work with them in other circumstances, but do you not have other point of views from a politics point of view?
Oh.
Really comply with Facebook?
Yeah, gosh, it's my way to, now it's my duty to think of all kinds of features and so on. This, I was telling you about development of the Facebook research lab. It has never been my, I've never been involved in contracts with Facebook and so on. Of course, as we know, there are many issues about the way these big American companies, now we can handle them at political level, fiscal level, cultural level, ethical level, whatever. Many ways, and with the current extremely powerful status that they have acquired. Very tricky problem in which one has to find a good solution. You know, we've been discussing a lot in France about fiscal issues and the fact that it should be taxation about the chiffre d'affaires, gosh, how do you say this in English? Yeah, and so on, and not the usual rules for the tax. Also, all these discussions within the new European regulation, the General Data Protection Regulation, about portability of data, about the right of not being profiled without being informed, etc., etc. These have become huge issues. It's we should, on the other hand, of course, not consider them as enemies because it would be stupid. And we should consider that there are, it also gives us information about ourselves. I mean, for instance, discussion with the researchers who went from universities to Facebook. By the way, my friend Yann that I was talking about, Yann Olivier, he went from university to the Facebook research, and many other people. And when you ask all these people, why do you move to the Facebook labs instead of remaining in the academia? Many of them tell us things like, oh, now that I have moved to this lab, I am much more free for my research. You know, this is very weird. We're used to the fact that if you go to the private sector, you have more money but less freedom. But actually, it's not always true, and this shows just the fact that we don't have enough freedom within our research units, and freedom can be also very pragmatic things on how to start experiment, how to buy material, whatever. And they also tell us how it's much more easy for me to do some experiments and start big computing to try my theory. And also, that's something we should be able to provide. So talking and seeing with this, with the research that is done with there, will be a very important way to make us improve in comparison. And one important part of the mission, one of the subjects that I will be discussing with Pascal Aucher from CNRS and other people, is how to set up the good facilities so that our researchers in this very highly competitive area, which has strong links with the industry also, are given some very attractive conditions for working in our laboratories, I mean, our public universities. And when I say attractive, it's not just a question of salary, it's a question of having just the tools to do your research as you want. Yes.
Professor Villani, what are your views on what people call the unreasonable effectiveness of mathematics?
Yes. It indeed is unreasonably effective. You know, when people talk about unreasonable effectiveness, often it is about the fact that it gives so accurate precision, in particular in some fields of mathematical physics. If you go to areas such as control fusion, in which nobody knows how to make it work and in which the experiment doesn't match with the theory, people will not find it so effective. But when you go in areas such as predictions by quantum mechanics, it's so amazingly effective that it makes you wonder. I like to think also that it's amazingly effective and unreasonably effective when you see that a certain tool in mathematics or idea in mathematics can go here, there, and in many other things. And sometimes you see a thing, you see, oh, it looks like the right concept. You don't know why, but then it turns out to be useful in many different contexts. So then it's a question of personal choice. Some people will say that's because we, humans, are exposed to many situations that become good at finding the concepts which are central. Other people will say that is because the world is written in mathematical language and so on. I like this second point of view, but you know, I don't want to impose my view on the others. And let us also say that there's another quote which I like, which is about the interaction between mathematics and life sciences. And that other quote by famous mathematicians says something, by Giancarlo Rota, says something like the lack of contact between mathematics and life sciences is either a challenge or a tragedy or a shame, something like this. And he said it's hard to choose which one. This was said some time ago. Now there are much more links between mathematics and life sciences, but still, one big question is that while the interplay between math and physics has been so extremely strong that physics has contributed mathematics with many deep concepts which have in turn been used in other problems of physics. In contrast, there are very few concepts which have been inherited in mathematics from biology. Neural networks is one of them, even though the neural networks resemble vaguely our neural examination, but one may say it's one of them, but there are very few of these concepts. So if you're it's important that when one says that, to recall that this quote about the unreasonable effectiveness of mathematics was coming from a mathematical physicist, I guess Wigner. And somebody involved in the biology application of mathematics may have said something completely different. Last question, maybe, the last one?
Yeah, well, there are two you have to select.
Okay, so here and there. Here first, and then we'll finish with the young one.
Thank you for a very fascinating presentation. Do you think one day will come when, thanks to artificial intelligence, computers are going to be able to do the kind of work you need to obtain your field?
That is the dream of artificial intelligence people, the artificial mathematician that will put us people out of business. I think, first, it's a question that people ask often. I think some of the reasons are first that AI people, some of them come from science, but many of them are also geeks, self-taught in some respect, and some of them fascinated by higher math, but saying it's not my business to do higher math, and playing with the idea that maybe they will be able to recreate this kind of artificial mathematician. Another reason is that you cannot think of an artificial physicist in the sense that physicists need experiments. While mathematics, it's only done in the, from some given axioms and you can try. It's one of the fields that is in which you can argue that maybe reinforced learning can play an important role by exploring all possibilities and trying to teach and reteach and so on. However, my personal view is that it will take a long, long time. There have been some experiments so far. We know that, for instance, some programs are able to recover the rules of classical Hamiltonian mechanics. Apart from that, and some part of classical Euclidean geometry, apart from that, I'm not aware of any significant straying thing. It's a debate we have from time to time with some of my colleagues, in particular with Stéphane Mallat. And Stéphane Mallat likes to say there will be a change in science, and artificial intelligence and big data theory, etc., will allow us to discover new theorems, new scientific fields, etc. But for the moment, it has not occurred. And you can even tease those guys by saying, you know, that statistical learning was developed in a sense, well, the way it developed in a sense was removing meaning rather than putting meaning in. It was like, let's forget about how things work and which is the cause. Let's just put a bunch of examples and see the thing decide by itself, by analogy, what is the output. And it could be argued that from purely scientific perspective, it is a regression. I think this only time will tell if there are some significant contributions in new science fields based on AI. There have been some new discoveries in science based on algorithms, mixing probability, optimization, whatever. For instance, recently, one example which I like, recently discovery by some biologists that there are actually 4 species of giraffe, not just one, was based on big Monte Carlo Markov chain simulations, Bayesian approach, running through the genetics of the giraffe. So it was really a mathematically oriented, sophisticated, mathematically oriented discovery in genetics. And it is very difficult for classically trained biologists, let's say, to explain how this discovery was made. But the problem was specified. It was, let's see how many clusters the genomes of the giraffes can separate into. It was not like, let's find a new theory for biology evolution or something like this. Okay, last question there.
Do you believe the way maths are taught in French schools is better or worse than in English schools? Young people study mathematics in university. Okay, tough question. Now, first, one thing to say is that you guys in French schools abroad are privileged. Usually, it works much better, the training in these foreign schools, French schools outside France, than the average inside France. Secondly, I have another mission currently. Besides the mission on artificial intelligence, I am part of a mission which is about the renovation of mathematics teaching in France. Now, my friends, it is very painful to recognize that in a country which boasts some of the great mathematicians in history and great pieces of mathematics, our education has become so poor that we are at the bottom of the international rankings within OCDE. And in particular with the training of the young kids. For instance, when you look at middle high school performance about mastering of fractions, you know, France has the lowest score of all OCDE countries, EOCD countries. It's a real shame. By the way, we also have disaster results in English speaking and disaster results in reading. About English, for some time we were competing with the Italians and the Spanish to be at the bottom, but I think we won the competition now. And yes, nothing to be proud of. So to come back to the math question, we will soon be giving back our conclusions and recommendations to the minister, and we will make some very tough recommendations. It's a whole system which is sick, and some of the problems are about the mathematics teaching, some problems are more general. The
more, how to say, the most painful is to see that solutions are known and not being used. It's the whole administration system, the whole governance, which is very, very sick. So then I think we will go through some energetic, I hope we'll go through some energetic reforms, which is the tendency that the minister has expressed he would do. It's just a start, and most important thing being to realize that France, even though its education system is thick, has a lot of goodwill, including a lot of passionate teachers, a lot of pride, and currently is in the mood of reforms and improvement. So I am very optimistic that we will do it. Thank you.